Hello guys, I'm Lin Kai from the group Hobby and I'm doing the dark side. So my research is on TextAttack, a framework for adversarial attacks, data augmentation, and adversarial training in NLP. So here's what I'll cover. First, a quick overview on TextAttack, then what an ensemble attack is and how my changes differ architecturally. I'll show practical effects on transferability, the experiment setup and results, the limitations, and finishing it with ideas for probing the research paper BBALFN, which is on a group or safe layer. So an overview of what the TextAttack framework is for. So here is the research paper with the example on how to generate how it swap words from a sentence to an adversarial sentence so that the sentiment analysis will classify it into something negative from positive by changing the word perfect to spotless. So TextAttack is a modular open source Python framework for adversarial NLP. It breaks attacks into 4 component parts. The goal on what the success criterion is, the constraints on what edits are allowed, and transformation on how to generate candidates, and the search algorithm to search for the candidates, to explore different candidates. Yeah. And so TextAttack ships with many single motor attacks and pipelines, so you don't have to rewrite the same script every time. It's built for reproducibility and chaining to generate, filter, search, and train. Before that, I will show an example on how to initialize the pipeline. So here is how you initiate the pipeline for sentiment analysis. So you load the augmenter, model, and the tokenizer, and the model wrapper. And then you generate the prompt with the model wrapper. Ask the sentiment classifier to classify the sentence as either positive or negative. Example, this sentence, this film is great, is classified as positive. Yeah. So my research is on Ensemble Attack. The core idea is to attack multiple models simultaneously to craft perturbations that transfer widely, not just a single victim. I rewired TextAttack from single model recipes to ensemble-aware attacks that purposely look for perturbations that transfer across models. So practically, I added 3 things. First, an ensemble model wrapper that loads many Hugging Face checkpoints and tokenizers and moves them to the device and returns the average logits per input batch. Here, it takes in a list and returns it in a batch, in an array. So here's a good example. Yeah. So the second one we talk about is ensemble transfer attack. It's a attack recipe that runs untargeted classification with beam search over that wrapper and uses a composite transform with the word swap mask LM and fallback word swap embedding with stable constraint. Third, enable ensemble transfer file from the scripts folder. It is the title script that has a CLI harness that accepts beam width, MLM candidate counts, max perturbation, device batch size, and writes example CSV logs for reproducibility. In summary, I turned brittle single model experiments into a flexible ensemble evaluation pipeline. So here's the Google Colab demo, which I will be showing you. This is the wrapper. It returns average. Then here's the ensemble transfer. Fallback. So basically, it does try word swap, and then it fall back into something. So here is the Python script for many parser so that we can initialize it like this. So we can run the script like this. Yeah. So the architectural differences So architecturally, the main change is the objective. So TextAttack normally optimizes one model's loss. My method optimizes the average logics across multiple models. That requires an ensemble model wrapper instead of a single Hugging Face model wrapper, and a recipe that tolerates API differences. The payoff is smoother loss surface and better cross-model transfer, where it is more general and less overfitted to a single model. And the running cost is complex, with n times the forward passes. The practical achievement I made in the file, in this file, ensemble transfer. So I'll be explaining what it does. So the expected outcome to optimizing the ensemble mean is a U perturbation that generalize better to unseen models where the heat shared decision boundaries. Hence, robust engineering is needed to incorporate multiple models. I had to make the recipe defensive. The different TextAttack forks expose different constructor signatures, forwards, swap. So the recipe tries several plausible constructors and logs but work. If MLM isn't available, it falls back to swap embedding. If neither exists, it fails to ensure that there is no silent zero candidate. On the experiment setup, for the dataset, I use this and the models. The goal function is still, as explained, is on-target classification. Search method is beam search. The transformations which I implemented, and then the constraint is the repeat modification, stop modification, max modification rate. Here are the parameters that I experimented with. And the query budget is the quality that asking for prompt. The max perturbation is a percentage on how many percent you can change the words in a sentence. So here are the results. It shows that conservative settings predictably failed because the search space was too tight. Relaxing the beam and MLM candidate budget and the composite transform, and the attack flips every label in my example test. But the success comes with cost. About 70 model queries per example, and about 19% of words change on average. You tune search for a trade-off between subtlety, cost, and transfer success. On the limitations on the ensemble model. So there are several limitations to this ensemble model attack. A single model attacks with cosine semantic filters tend to have higher semantic similarity so that it changes the meaning less. Ensemble composite attacks uses MLM and embedding produce fluent swap but can cause semantic drift where the examples that read fine but invert meaning. Other limitations include heavy computation with n-time forwards complexity, blur disagreement signals, and unreliable evaluation metric with label flipping since it ignores fluency, meaning, and downstream coherence. Mitigation include expert cosine checks, weighted ensembles, and human evaluation. But as for now, human evaluation is still needed on most part for the semantic similarity on results with high success rate. Because even when the attack has a 100% success rate, it doesn't mean it's humanly believable. The next step is moving from statistical misdirection to true semantic deception that is subtle enough, not about raw label flipping success. So I'll give an example from the code. From the script attack benchmark, I tried it on certain tests, like show result of a single model attack versus an ensemble model with single model and ensemble model with 3 different models. So the first one is the single model, which is what TextAttack does without my modification. I use 5 examples since I showing 5 examples. So here's what it substituted the words. And it's the analysis, the sentiment classifier is classifying it from positive to negative. Black, bleak, and desperate is being swapped to eerie and sorrowful. And then this is the one, sounding, noise, and staggering. Okay, still fine, but then this doesn't really make sense. Still, the classification classified it as 100% success rate with 26% of words perturbed. For the single model on my Ensemble Attack, this is how it swapped the words charming, I think, to long and difficult. But on some tests, it failed due to the beam search not able to pass the constraint check. And so for this, from astounding to chosen, which doesn't make sense in a humanly way. But then there are this slow to moving and fast, which the opposite, which doesn't make sense and cannot fool a human. Doesn't make the same. I mean, it doesn't have the same meaning. But the accuracy is 40%. Under attack, success rate is 60%. And for the assemble model with 3 different models that I tried with this model, and it's performing a lot better, charming, attracting, and long and difficult. Bleak, desperate, it changed to beautiful and hopeless, which makes sense, kind of. It failed on this one. And on this astounding and astute, it swept to chosen and joyless. For this, it's still not performing well, but the success rate is 80%, which is performed much better compared to a single model. So here, that's all for my research. Now you'll be talking about attacking this paper, attack strategies against BBALFA, the defending against lateral attacks by layer-wise feature analysis. I'm attacking the group safe layer to clarify that. So here's the paper, and I have 5 strategies which I propose. So the first is angular alignment to add the secondary training objective that forces poison sample features to align directionally with the binding central in the layers of interest to minimize cosine distance. So why it works is that the detector flags inputs because their feature direction differs. If an attacker trains to remove the angular gap, the detector loses its signal. The second strategy is the multi-layer or distributed backdoors to spread trigger signals as many tiny perturbations across several layers rather than a strong signature at a single layer of interest. The paper's method looks at the LOI and with the 2 preceding layers, and the distributed encoding reduces difference per layer. The third strategy is the sample-specific dynamic triggers that use per sample or adaptive triggers tuned to avoid clustering or centroid alignment. Why it works is that it is hard to cluster or align to a centroid, but also may be less consistent, so LOI signal might be noisier. The fourth one is the clean label attacks with minimal visible perturbations that insert poisons whose labels remain correct and whose perturbations are subtle, designed to nudge model internals without causing large feature shifts. It works because the detection that relies on large directional shift may miss very stilty perturbations. The last one is on label clipping or validation corruption. It corrupts or manipulates validation labels used to confuse centroids or thresholds. This works because centroid estimation uses mislabeled validation data. The LI choice and thresholds gets corrupted. So here's all for my presentation on my research. Thanks.